Next, we move to game theory. This is the first type of tools that we'll use later. I'll start with some examples, then I'll introduce notions of game theory, and in particular, potential games that will play a very important role in this tutorial. So what is a game? A game is a situation where there are several actors. Each one has to choose some decision in order to maximize his utility, but his own utility depends also on the decisions played by others or chosen by the others. So here are some examples. Consider the situation in which we have several PCs connected to the network via Wi-Fi. Now each one of them upon arrival has to decide to which access point to connect. The utility that a user tries to maximize is its throughput. It gets the information from the network on the quality of the channel to each one of the access points. It has to decide to which access point to connect. This is the standard association problem. A more complex association problem is the one in which we have to decide whether we connect to Wi-Fi or to a cellular phone network. A second type of problem is the routing game. In a routing game, the individuals have to decide what route to take. If the decision maker represents a network provider, it has to decide how to split its traffic between different routes. Now, one can consider either the cooperative case in which one minimizes the global cost, or non-cooperative case in which each individual minimizes its own costs. Here is an example from road traffic. This is the Belt Road around Amsterdam. Each driver can decide whether it goes clockwise or anti-clockwise to its destination over the belt. The decision will rely on the estimation time. If the drivers had the exact time, it could cause big oscillations. The engineering problem here is to design the signaling that will be used in order to avoid these oscillations. This type of game is usually modeled using a continuum infinite number of players, of drivers. So we shall next look at a more detailed game in which there are finitely many players and each has finitely many options of actions to take. This game is the well-known prisoner's dilemma. There are two players that are suspected of a crime, Emile and France. Now, if both admit, they will each go 1 year in prison. If both don't admit, they get 10 years in prison each. If one admits and the other doesn't, then the one that admits gets 15 years, while the other one is freed. Here it is assumed that every one of them wants to be as little as possible in prison. We represent this story with a matrix. The red entries in the matrix are the cost for Emile in terms of years in prison, and the black ones are those for France. The key issue here is to find stable solutions. Solution 1,1 is unstable, because each one of the two persons may try to improve it by deviating. The only stable solution here is 10-10, where both don't admit. This type of stable solution is called Nash Equilibrium. It is a solution in which no player has an incentive to deviate unilaterally. No such deviation would improve its situation. An alternative concept of optimality is the Pareto Equilibrium. It is a cooperative type of definition, a dominating solution. It's defined as following: there is no way to improve the performance of one player without harming another one. In the prisoner's dilemma game, we see that all possibilities, except for the one that is Nash equilibrium, are Pareto equilibrium. This means that the Nash equilibrium is quite inefficient. It is the only one that is not Pareto equilibrium. One paradox here in this prisoner's dilemma is the monotonicity paradox. Assume that we change the 0 to 5. A prisoner that does not admit is always punished. For example, just imagine that we may have some prior information that the crime was committed together. So by increasing this punishment, by giving more years in prison, 1-1 becomes a Nash equilibrium, which is a Pareto solution. Increasing costs can result in a better performance, in a larger utility at equilibrium or in a lower cost at equilibrium. Equilibria do not always exist. Here is an example that we call a zero-sum game. There are two players. One plays the top or bottom line, and the other the left or right columns. The utility for player 1 here is always minus the utility for player 2. The sum of these two utilities is always 0. This is why it is called a zero-sum game. In this game, player 1 wants to maximize the red entry, and player 2 wants to maximize the black one. There is indeed no Nash equilibrium here. For example, the top left solution can be improved by player 2 if it deviates unilaterally to R. We now consider some generalization of this game. We assume that instead of choosing a row or a column, each player can choose a probability of choosing a column or a row. That is, player 1 can choose a probability of playing top or bottom, and player 2 chooses a probability of playing left or right. Now, instead of maximizing the utility of the policy, we now assume that each player wants to maximize its expected utility. Let us denote by P the vector of probabilities for player 1, and by Q the vector of probabilities for player 2. Then the expected utility for player 1 is U1, so it is the red matrix multiplied by the vector P to the left and by the vector Q transposed to the right. So it is PUQT. With these definitions, it is seen that the Nash equilibrium here is to choose the vector whose entries are 1/2 for both P and Q. This generalization has the advantage that every matrix game has an equilibrium if we use here the space of mixed policies or randomized policies. Consider a vector of actions for all players, denoted by A. For this A, we define JIA as the utility function for player I. We define A minus I as the vector obtained by omitting the action of player I from the vector A. Now, for that vector A, we define the concatenation of A minus I and BI as the new vector that is obtained when every player J sticks to AJ, except for player I that changes from AI to BI. Given a vector A, AI is said to be a best response if it optimizes the utility of player I when all the others stick to their policy AJ. A Nash equilibrium, then, is a vector A such that each player is playing its best response against the policies of the other players. Next we move to games where the set of strategies is not discrete anymore. It is convex compact subset of real valued vectors of some finite dimensions. We shall use the following theorem of Rosen for the existence of equilibrium. If the utility of player I for each I is concave in the actions of that player and continuous in the action of the other players, then there exists a Nash equilibrium in pure strategies. By that I mean we don't need to randomize or to use probabilities in order to reach a Nash equilibrium. So here is an example of such games, of Rosen games, which are called concave games. This is a power control problem. We assume that there are immobile terminals, and each one controls its transmission power Pi to a common base station. So there is one base station that is common for all mobiles. We assume symmetric Gaussian channels with no attenuation, such that Pi is also the received power from terminal I. As before, we consider the throughput for player I as its utility. Now, Shannon theory gives us an expression for the throughput that player I can achieve. It is given by log of 1 plus signal to interference and noise ratio from player I. Now, this signal to interference and noise ratio is the ratio between the power received from player I and the total sum of powers of the other players Pj and the terminal noise N. The utility for player I is in fact given by the difference between the throughput of that player, and the cost, the energy cost, which is assumed to be just proportional to the power that it uses. Now we see that this J, this utility for player I, is indeed concave in Pi and continuous in Pj, and therefore indeed a pure equilibrium exists. Now here are some very important properties of utilities in game theory. So the first thing to note is that the action of player I that maximizes its utility for given actions of other players is unchanged if we add to JIA a constant. In fact, it is unchanged even if we add to JIA a function of the actions of any other player than I. It is also unchanged if we replace the utility for player I by any strictly increasing function of that utility. So here is an example that is taken from the power control game that we had. So first we denote by absolute value of P the sum of the component of P, of a vector P. Next we shall show how these properties allow us to actually solve the power control game that we just saw. In fact, this will be done by transforming the game into a global optimization problem. To do so, we first add to the product of G times Pi also G times the Pj for all other J's. The second step is obtained by writing the logarithm of a fraction simply as the difference between the logarithm of the enumerator and that of the denominator. And then we observe that the logarithm of the denominator does not depend on Pi. Therefore, we can just delete it, which means that we added a function that does not depend on pi, which again doesn't change the maximizer of the utility in terms of player I. So after these two operations, we obtain an equivalent problem of maximizing the difference between the logarithm of n plus the sum of pj's minus the product of g and the sum of pj's. The interesting and important thing here is to note that this maximization is of a utility that no more depends on the player I. It is the same for all players. This means that we managed to transform the problem into a global maximization 1 instead of a game, which can now be solved using standard techniques in convex optimization. Any solution to this convex optimization problem gives us a Nash equilibrium for the original game. This function v is known as a potential, and games that have a potential like this one are called potential games. Here is a more formal definition of a potential. V is the potential of a game if for every player I, every vector of actions A and any deviation for that player I from AI to BI, the difference of the utility of player I evaluated at A and evaluated at the deviation from A equals to the same difference between the potential at A and the potential at the deviation from A. Now, if the potential V is differentiable, then this definition is equivalent to the following. The partial derivative of V, of the potential V with respect to AI, should be equal to the partial derivative of the utility for player I with respect to AI for every vector A and every player I. When we deal with games, we are interested not only in the existence of the equilibrium, but also in its uniqueness, as well as in convergence to the equilibrium. Let me say what I mean by convergence to equilibrium. Assume that we have a sequence of couples Tn and In, where Tn is an increasing sequence of times, and In are a sequence of the identity of players. At time Tn, player In updates its policy by using a best response, or something that is called a better response. We assume that each player appears infinitely often in the sequence In. If it is indeed a potential game, then a change of a policy by a player results in a higher utility to that player, if and only if it results in a higher potential. This implies that any sequence of best responses of the players converges to a local maximum of the potential in a finite time. If the potential is strictly concave, then it has a unique local maximum, which is also a global maximum. Therefore, there is a unique equilibrium, and any sequence of best responses of the players converge to it in finite time. We next present a potential game that occurs in a discrete setting, where each player has a finite number of actions. In this example, we speak about minimizing costs instead of maximizing utility. The game is known as the congestion game. It is a special case of the congestion game, in fact, introduced by Rosenthal. We consider this game in a topology of parallel links. There are m parallel links between a source S and a destination D. We assume that each of I players have one unit of flow to ship, and that each player has to decide through which link to ship this flow. It cannot split the flow between several links. Let x of m be the total flow sent to link m under some action vector. The cost to ship a unit of flow through link m is assumed to have the form, it's a function only of that link and of the total flow that goes through that link. In particular, it is assumed not to depend on the player I, so it is the same function for all i's. Now assume that player I decides to change from link k to link n. The difference between the costs for player I before and after deviation is given by the first equation in these slides. It is the difference of two terms. The first corresponds to the cost before the deviation, and the second to the one after deviation. This game turns out to be a potential game, where the potential is given in the last equation in this slide. It is the sum of local potentials over all the m links. For each link, the local potential is simply defined as the sum of link costs of that link, m, over j varying from 1 to the total flow under the policy A in that link, xm. Now the conclusions from the fact that we have a potential here is that the pure equilibrium indeed exists, that local minima of the potential are the equilibrium for the game, and that if link costs are convex, integer convex in fact, then there is a unique equilibrium and any best response sequence converges to it. We are now ready to introduce the first problem related to content dissemination in a social network, that of deciding what content to specialize in. We assume that there are m types of contents and I content providers. Each one of these content providers has to decide in what type of content to specialize. The utility of a content provider I, if it specializes in content type M, is a function that depends only on the type of the content and on the number that specializes in it. So it is this function f of the total number xm that specialize in M. It is assumed to be strictly concave decreasing. Indeed, the more CPs specialize in a content M, the less is the revenue of those that specialize in that content. Under these assumptions, it turns out that there is a unique equilibrium in pure strategies to which any best response sequence converges. So this, in fact, is a direct result that is obtained by mapping our game to the congestion game of Rosenthal, in which a content provider is a player and in which the type of content it specializes in maps to the link that a player uses in the congestion game. We next introduced another potential game, the generalized Kelly mechanism. It will play an important role in our tutorial later. Some resource that contains some C units of good is to be split between I players. Each player I makes a bid AI. Its utility is related to how much it receives. It receives an amount which is proportional to its bid. It receives DI, which is defined below, as AI divided by the sum of AJs over all J times C. So what it receives is just proportional to its bid divided by the sum of bids of everybody. If at least one had a positive bid, otherwise everyone gets 0. In addition, it has to pay some cost proportional to its bid. The utility of a player is thus the difference between the payoff, which is some utility U that depends on the amount DI it gets, minus the bid AI it proposed. The utility U may change from one player to another. As mentioned, this game is also a potential game. The potential is given as the sum of local potentials, again, where a local potential of player I is given by the first equation in this slide. The potentials are concave continuous, and therefore the equilibrium turns out to be unique and has all the good properties of a potential game. This potential was obtained by Bruce Hayek and Gopalakrishnan. It was reported by them in a conference in an oral presentation. It appears explicitly later in many places with proofs in some. For example, Johari and Sisiklis report this and provide the proof in Mathematics of Operations Research 2004.